Good evening, everyone, and welcome to today's webinar. I'm Uma Maheshwari. So, first of all, I would like to thank Young Indians and Yuva, the student wing of Young Indians, for helping us to connect with a larger audience. Today, we will be focusing on the topic deep learning algorithms in automotive solutions. So, before we get into the details of the session, we would like to give you a glimpse of what we do in the field of automotive.
We are an automotive technology company providing software solutions for in-vehicle infotainment systems and instrument cluster. We have been able to bring life to the infotainment systems of the new generation versions of Volvo, Mercedes-Benz, Porsche, and Ford with more than 6 production programs. We are headquartered at India and have development centers in Japan, Sweden, and Germany. With more than 200 engineers, we support our customers throughout the journey from conceptual design, implementation, optimizations, and certifications to maintenance. We are an ISO 27001/2015 certified company and ensure strict compliance of automotive Sparse. Also, the project had several challenges such as third-party app store, internet connectivity, over-the-air update, which were first time in industry. We could successfully overcome the challenges and were awarded a grade by the OEM audit. In our current instrument cluster development program for a North American OEM, our scope was to develop the full instrument cluster software stack and HMI in Kanza for 5 variants. We could achieve some of the critical challenges like fast boot optimization and real-time graphics. Our expert team with 300+ man-years experience makes us uniquely qualified to serve any specific needs of the automotive industry. To cater to the future needs of car makers and Tier 1s, our R&D team is focusing on computer vision, machine learning, deep learning, 3D visualization, and data analytics. Quick ramp-up, a perfect culture match, high productivity, and great quality are the characteristics that reflects Axia's approach to business.
As you have seen, Axia provides a wide range of automotive infotainment solutions. In a nutshell, we can say that we drive the future of vehicle experience. So I'm pleased to introduce a speaker, Rinal and Chetan, who are joining us from Trivandrum. Rinal is an expert in deep learning and holds a strong root when it comes to knowledge in programming languages like C, C++, and Python. So he's one of our strong hands behind our AI-based driver monitoring system. Chetan, he is an expert in machine learning and deep learning. He is well versed in both supervised and unsupervised learnings and holds strong basics in many programming languages, including embedded C and Python. He has done many valuable contributions in our AI-based driver monitoring. So we would love to hear from you during today's presentation. And if you have any questions for our speaker, please feel free to send it through the YouTube comment section. We'll be answering the questions by the end of the session. Okay. So make sure you are connected to our social media pages like Instagram, YouTube, and LinkedIn so that you don't miss any of our updates. So without further delay, I welcome our speaker, Mrinal and Chetan. Over to you.
Thank you, Uma. Today's session is about deep learning algorithms used in automotive solutions, which will be a continued session of our previous deep learning algorithm sessions. So going to the contents or topics, what we'll be covering in this webinar is there will be a detailed explanation on artificial neural networks and convolutional neural networks. And then we will build a deep learning model using Keras sequential API in Colab, which is available open source. And then there will be a explanation on popular deep learning models like VNet5, VGG16, GoogleNet, Inception V1, and MobileNet V2. So going to the detailed explanation on ANN. So let us go to this where we can not only learn, we can experience the deep learning. This is a portal where you can experience how a neuron will be responsible in a machine learning, deep learning model to generate some prediction or classification. So here you can see we have selected a classification. That means this uh, neural network will be a classifier, and we have a learning rate of point 0.1. So uh, so this session will be, as I told, it will be a bridge between the previous one. So here you can see there are two layers of neural network. So if we can build it from scratch, so so this classification problem we have to solve, and this is the data distribution which we have to classify. So you can see there are blue data points and orange data points which we have to differentiate or classify. So X1 are the X1 and X2 are two features of this data distribution. So since it is a two-dimensional data distribution, we are just using it directly. So you can see if we using proper linear uh, learning, we can't basically classify these. So we'll add a layer of neural network which has through two neurons, or else we can make it three. So we'll try to make this system learn with having these three neurons. Let us check whether it will be able to learn or not. So if you click this button of run, like learning will start. So so you can see the the neural network is somewhat able to differentiate or classify between the data points. But this seems like a rectangle kind of classification in the center. But we need a better classification. So what we can do is we can experiment adding another layer of neural network. So here we can add another neuron and just check whether it will be able to learn. So after it learns, we'll be able to see the weights of each. We'll be able to see each weights, and we'll be able to see what contribution does one neuron or one layer of neurons will be there for classifying the problem. So let us train this. So as you can see, we have a better classification between two classes. So what this basically tells is like the architecture being more robust, the classification will be very precise. So as you can see, this neuron is contributing only classifying whether about the data belong to a blue class or a orange class. And then like you can see all of these are mostly doing in the first layer. All of these are mostly responsible for classifying different distributions of blue class. So here, when you can see the second neuron in the second layer, so you can actually see this gets all the input from the combination of the previous all the hidden neurons. So it will combinedly produce it will be able to recognize a bigger feature which will be responsible for the classification. So if we can just experimenting, if we can add more neurons and we can check how that basically learns and how better we would get the result. So as you can see, the result is okay, but not very much improving. So we can add one more layer with very less neurons. So we can experiment this with this neural network. So you can see the system is able to differentiate very very robust compared to the previous. So like this we can visualize, using this we can understand how a neural network learns and works. So you can see here in the first layer, it is just picking up some linear distribution of that data points. And our problem is not linear classification. So the second layer, it identifies some non-linear behavior of this data, and then it will try to generate a very good, it will try to classify the data quite better. So, and there are so many other parameters in this which you can play with. So let us try changing the activation function in the output layer. So there are a few activation functions which you can play with. Let me just select a Sigmoid activation function at the output and check how better our results would be. So as you can see, a sigmoid activation function doesn't work in this case because it is a very non-linear or else it basically scales the data down. So let us try some other activation function, tan h, hyperbolic tan. So here you can see the classification is pretty good, and here in each layer you can see how the classification is going up, how it contributes to the final classification. So this seems a pretty good result. So this is a robust model now. So but still, for getting a better performance, we can reduce some of the nodes or we can reduce the complexity of the model by using some regularizations. So here there is option of regularization as well. So you can select either of L1 or L2 regularization. So let us try having a L1 regularization. So these methods of optimizing, which will be discussed in some future sessions. I'm just giving you an experience how this works now. So let us train this with L1 regularization. So you can see this regularization is not suiting this. So going to L2 regularization, we can see that the model learns, like this regularization helps us to point out the neurons which uh, will not contribute to the classification basically. So what it will do is it will basically check all the weights, and it will check which are all the neurons which are responsible to generate to solve a problem, and the nodes which are which has very less weight, it will nullify the weight of those. As you can see, this neuron is not contributing to our classification. So if we reduce this five, in this first layer we have five neurons. If we reduce one neuron and train, we still get the same result. So that's how we can learn and experience the deep learning in this. So this is more of a very representative thing. So let us go to a real-time problem, which is again we can experience it as a graphical one. So this is again a portal where you will get a chance to classify the handwritten numbers. So this is the window where you can write the numbers, like handwritten numbers, like 2. I'm writing 2. So this model, what they have used is a convolution neural network, which has two-layered convolution and pooling method, and a flattened layer and two dense layers. So you can see this, whatever we have written, it has been converted into a pixel-based picture. So this layer this layer is actually our first convolution layer. As you can see, each of this pixel has been convolved with a matrix with a kernel on the image. So these the value of the kernel can be it will be learned over training. So what basically it does is it tries to extract some features from the actual image, and then it will try to retain those features for our further computations and things. So this is about the first convolution layer. As you can see, the entire feature extraction of this convolution has been you can see how it has been evolved and how it has been learned. So this basically has six features, which means six kernels will be individual kernels will be convolved on these image. So from this, we will use a pooling method, which can be a max pooling method or average pooling method. So here, based on the kernel size, we will reduce the number of pixels. That means we reduce the size of the data without losing any features, without losing any major features on the image. So you can see here this point of data is being extracted from four values from the previous convolution output. So here we reduce the size of data and still we retain the information. So from this again, so considering this as a very minute features, we can derive many other relation between these features by adding another convolution and pooling methods, another convolution and pooling layer. So here you can see these again are being extracted from the previous layers output, and it is again the convolution with some kernel size. So doing the convolution and max pooling or pooling, average pooling, what it basically do is it will help you retain the same information from the actual image in a very less data. So that how it helps. So you can see even this is a average or a max pool layer. So it is actually this layers are now for having this layer. This will be the final layer of our max pooling, and then this whole uh, output of the second max pooling layer basically, it will be flattened out and then given to a dense neural network to learn these features. So this convolution layer pooling layer basically helps us extracting the features from the image. So from the image or any other complex data. So we will flatten this, which is not like it is not visual, but when you see on this, this is a dense layer actually. You can see this each dense unit is actually connected with all of the previous max pooling data. It has been basically flattened. So this is a first layer of dense network, and there is another layer of dense network which will again learn features generated from the previous network. You can see it has been connected with all neurons with the previous layer, and the weights have been indicated on the brightness of the line. So you can see how these are connected. These are basically a dense connected thing. And then there is a final layer which has only 10 neurons, which is the output layer. So when you give a image input of handwritten number, so there will be some of the neurons which will be activated here at the output layer. So those represent your prediction. So from this basic from that layer, the output will be, you will have to consider the output. So you can see when we have written 2 in the draw box, we can see the first guess what the neural network, the convolution neural network has guessed is 2, and the second guess is 1. So we can try out with some other number like 6. Let us try with 6. So you can see at this time it has the first guess goes to 8. So which means this model has not been trained with proper, like with variety of data sets. So we can make this model predict this as 6 by giving some data sets which are kind of similar to this whatever we have written on the draw box. Let us check with 7. So we can see 7, it is able to classify it as 7, the images. You can see which are all the neurons which get activated for a particular input. So you can basically this is like a very representative and a very, we can actually experience what and all things are happening in the convolution layer. So at this basic stage, going to this and playing around it would help us very greatly. So I hope you experience the neural network working and the convolution neural network working. So we can go now build a neural network based classifier for for a very good interesting problem or a data set which is called fashion and mist data set. So this part would be coding. So you would be needing some prior knowledge on Python, and we are using Keras sequential API and TensorFlow in the backend. So this what I'm using is a Colab, which is a freely available tool from Google, which everybody can use if you have a Google account. So here here you will be allocated with a server based CPU and GPU and memory. So you can run your code even though if you don't have a GPU. So you can set that in the notebook settings where we can select GPU and save. So now our code will execute on the GPU. The training will be done on this GPU. So you can see the system has been connected with the remote server. So basically Keras is a higher level API given for deep learning which uses TensorFlow in backend. So these are all some imports which we'll be doing. We'll be importing some libraries which are TensorFlow, Keras, NumPy, and Matplotlib. NumPy is basically for data reprocessing and manipulations, and Matplotlib is for graphical representation, or if you want to plot something, uh, Matplotlib would be helpful. So, as I told you, we'll be using a data set called fashion MS data set. So what does this data set contain is, this has 70,000 grayscale images. These have been already classified as into 10 categories. So we have 10 classes to classify into. So each of this image is actually a 28 cross 28 pixel. So it is quite lower resolution uh, picture, but you can see still our system, what we build, a deep learning model, what we build will be able to predict what class it belongs to, what category it belongs to. So if we are we can import this. We can load this data set basically from the keras.dataset.mnist fashion mnist dataset. So this will download and load the dataset into the memory. So here we divide the whole data set into train image and test image, and the labels. The labels are actually uh, to a image. The corresponding category is called a label. So in supervised learning, we name it as label, as like it means what the model you want the model to predict. So basically, it is like actual output what you are expecting from the model. So we load this data set into tuples, which are train images, train labels, and test images, test labels. So here you can see how what all the labels corresponding to the class. So label 0 means it is the image belongs to a t-shirt or a top. Label 1 has trousers, and label 2 as pullover, and there are 10 classes which you can see. So here we will just uh, store these class names into a list for our future references. So we can, as you know, we loaded the data set. We can just recheck whether the data set what we have loaded is. We can check basically the shape. So we have to have 60,000 images, each of 28 cross 28 image. So as you can see, it is 60,000 comma 28 comma 28. So it is perfect now, and we can check whether we have labels for all our training data. So we can just check the length of the train labels, which has to be 60,000. So it is 60,000. Then so each you can check each label will be in between 0 to 9, which is like 10 classes. So we will check the shape of each image, or like test images, how many test images we have. We have 10,000 test images, and again they are of 28 cross 28 image. So you can see we have 10,000 test labels as well. So we can just check one image how it is. So you can see uh, this is actually a picture of a shoe. So this is how you can see it is 26, somewhere 26 comma 26, and this is a grayscale image, but it has been pasted into that. So before we build like we give the data raw to the model, we'll have to scale or normalize the data, so that the higher the input with higher values will not be given higher privileges, something like that. So we will normalize the data set by dividing them by 255, because each pixel is a 8-bit 8-bit number, a integer, which is 255 to the max. So we divide it by 255. So here you can see we display some of the uh, images along with their classes. So these are all just some 25 pictures what we have uh, in the data set. So now we have pre-processed, we have loaded the data set, we have seen what is inside, and we have scaled it or normalized the data set. So let us now build the model, which will be a very basic model using the sequential API. So uh, building a sequential API, as you can see, it is quite simple. You can use the keras.sequential API and just add layers in the list. So we are using the first layer as flatten, which flattens the entire images. For example, if it is 28 plus 28, it will just flatten into the number 28 into 28. Then we have a dense layer of 128 neurons, which has the activation of ReLU. And then we have a dense a layer of 10, which basically is our output layer and gives us and it learns how to classify between those 10 classes. So this is our model. Let us build the model. You can just click this run button to run a cell. Uh, so after building the model, we have to compile the model. We have to compile the model telling what the loss function has to be used while training, what the optimizers have to be used, and what are all the matrices it has to use to display while the training. So you can see here we are using a Adam optimizer. So it is quite well performing. It is a very good well performing optimizer. So it has we will not go into deep of Adam optimizer. Then the loss function will be sparse categorical entropy, cross entropy. Why we are using this? Because we have multiple classes. We have multiple classes of label. So we'll be using a sparse categorical cross entropy. And the matrices, we are just mentioning that we need just the accuracy. So after you compile the model, you can just use model.summary to check how your model is being. You can check the architecture of your model, and you can check what are the parameters in the model. So executing this block, you can see here we have a flattened layer which produces the output of 784, which is 784, which is actually 28 cross 28. And we have a dense layer of 128 units, which has parameters of around 10 lakh or it's 1 lakh. So then dense one, there is another dense layer, which is actually our output layer, which again has 1290 parameters. So you can see whether these parameters are trainable or not as well. And if you go deep into building models, if you want to explore more, you can actually freeze some layers and do many stuffs like that. If you freeze a layer, those layers parameter will come into non-trainable parameters. As you can see, we didn't freeze anything. We did everything by default is not freeze, so we don't have any non-trainable parameters. So training the model, there is a function called from the model called fit. So we can just call that function giving the data set where we have the train labels as our image input and the train labels as what it has to be, what it has to predict. That means the label corresponding to the training images. So we will just train it for 10 epochs. The epoch means how many times you want to expose the data to the model. How many chances you want to give the model to see the data. So so let us start the training. So as you can see here, we are getting an accuracy on test on the training data set of 82, which would gradually increase as the number of epochs go on. You can see the accuracy is getting better. We reached 89 and we crossed 90 as well. So after the training is done, the weights will be adjusted to evaluate or test the model. So now only the training data set has been exposed to the model. As you know, there were 60,000 of training data set, and there were no. We had another data set of tests which were not exposed to the model. That means now we will be testing the unexposed data set on this model and check what's the test accuracy, how accurate it is on the test data set. So you can use model.evaluate function to evaluate the model. So you'll be giving again a test image data set and a test label. So it will calculate the accuracy. So you can see here we are getting 88% accuracy for the test data set, while our trained data set has 91 percent accuracy. So this is a great. Great means what I mean is if the difference between these two are very high, then the model has overfitted or some issues with the model. So you will have to redesign its architecture, and you have to use some optimization techniques to reduce. So evaluating a model has been done. So we got 88% accuracy on the evaluation data set. So let us make some predictions on some of other images. So what we will do is we will load the same model what we have, and we will we'll use a softmax output transfer function activation layer, so that we can have a probability on each predictions. So this model.predict will basically give you the result of the uh, input data what you have given. So we this input image is actually test images are actually our input image. So we'll get the predictions, and we'll check how each predictions will be. So as you can see, there will be a 10 float values or a 10 probabilities of each predictions. So what it means is the model will predict with the how probable the input might belong to a class. So we should consider the highest probability result as our result. So you can see we are using NP max, which reduces the whole thing into a maximum, and it will tell us what index it belongs to. And you can see here we got the ninth index, which is the highest. So which is almost 97 something, 97 like nine. It is zero point 0.9 probably. The probability of the prediction is uh, 0.9, which is quite accurate. So let us check whether it is the same in our test label. So it is correct. That means the model has predicted uh, correct results. So this is now we can just visualize how like against the images how our model will be behaving. So here we use zeroth index image of test image, and we will just see it is just a pictorial representation of previous what we saw the predictions. So you can see this is a boots ankle boot, so which belongs to the last class, ninth class, and this is the probability distribution of the predicted output from the model. You can see the model has predicted quite accurately that it belongs to the ninth class, which is ankle boot, and the and it 97% is its accuracy to the its classification. That accurate it is. So this there is another image you can see, which is actually sneaker, which it belongs to sneaker class, but it has been classified wrongly. So we'll have to use some robust architecture to solve this problem. So as you can see, the model prediction would be not always 100% accurate. There will be still some errors or some wrong predictions. As a AI engineers and uh, data scientists, it's our responsibility to make them predict correctly or design their model architecture so that it will predict correct results. So finally, we will just see the predictions against some images, and we will check how good it is. You can see the predictions are quite good. Only one case where it has predicted as bag instead of sneaker. So I think here we learned how to build a basic classifier model against the fashion wellness dataset. You can try this out going to TensorFlow's official web page. So I hope you got how to build a basic neural network or a deep learning model, and experiencing how the neural networks work also was quite interesting. So I'll hand over this session to my colleague who will be explaining you further topics about popular deep learning methods what are used. So over to you, Minu.
Thank you, Chetan. So, hi all. We'll be starting from the timeline of the some of the architecture, CNN architecture. I hope you have got idea from the demo what Chetan gave. Like you can use such type of basic model to detect a classifier or a object detection model. And if it comes to the automotive sector, in Axia we have developed the DMS module, and we have used several such models, custom models to detect drowsiness detections and emotional detection and other types of detection systems. So first I will go through the timeline of some of the CNN architecture. If I go first to the 1990s, first Lean 8.5 was introduced, and Yan LeCun and Dr. Li Bo and Bengio and Patrick Hafner proposed this type of neural network first, and it was a very simple network. In the later on of this session, I will be discussing of this Lean 5. And when I go to in 2012 or 2000, between 2012 and 2013, uh, there's another CNN network was designed by Alex Greenvesky, which is basically uh, a visual recognition. In visual recognition challenge, it was introduced in 2012, and in 2014, VGG16, which is also stands for Visual Geometry Group, was proposed by Karen Simonon and Andrew Giserman. And in 2014 again, the Inception V1 or Inception model, which is Google, which is also named as GoogleNet, was introduced by Google. And then RaceNet, which is known as a residual network, in 2015 it was introduced. And previously, after Inception V1 model, V2 and V3 and V4 was also introduced. And then the exception, which is adaptation from the Inception, as the name suggests, it was introduced in 2016, and ResNext in 2017, and it is also related to the ResNet. So now I'll be explaining to the Linet 5. We'll be getting into the next slide of the Linet 5 architecture. So basically, this is a seventh layer network, and number of parameters is about 60,000 in this network, and input say shape is 32 by 32 with a single channel. That is, you can give input a gray scale image channel. And linear architecture is very straightforward and small. It can run on CPU also. It doesn't require a GPU. If you give GPU support, then the FPS and the accuracy should increase. And in this architecture, find first convolutional layer with 6 feature matrix have size of 5 into 5 and a stride of 1. On the below picture we can see. And the second layer is the average pooling layer or sub sampling layer with a filter stride of 2 into 2 and a stride of 2. And this results the image dimension to reduce into 14 into 6. And when I come to the third layer, this is a second convolutional neural network layer with 16 feature matrix. And the fourth layer is a average layer with a filter size of 2 into 2 and a stride of 2. And the fifth layer is a fully connected layer with one with a 120 feature map, each size of 1 into 1. And the sixth layer is fully connected layer with more than 80 units. So, and the last is output layer, which is again a fully connected softmax output layer with the 10 possible values. And if you go to the data set of to detect 0 to 9 handwritten letters, so you can at the output layer you will get the possible output of 0 to 9 uh, numbers. So this is the overall explanation of the very basic architecture uh, that is LeanEd 5. Now we'll be discussing about the VGG16, which is also a very important architecture. So this is also a 16 layer network, and the 16 VGG16 stands for the 16 weighted layer. And here the input size is 224 into 224 with a 3 channel. So you can give RGB images as the input. And this model achieves a 92.7% on the ImageNet dataset, which contains 14 million images belonging to 1000 classes. So in this, if I go deep into the architecture of this VGG16, the first 2 layers have 64 channels of 3 cross 3 filter size. And I will not go deep into the each of the architecture and explaining that, because first I have explained it on the LeanEd 5. So I'll be giving an overall view and over what are the applications of these architectures. So generally it is used for object recognition and image classification problems, and the number of parameters in this architecture is 138 million. And in VGG16 is one of the best performing architecture, which in the that IVS VRC challenge in 2014, which has a classification error of 7.32 percentage, where Google Net has competed with the classification error with 6.6 percentage. And basic challenges is it is very slow to train, and the size of VGG16, which is based on ImageNet weights, it's very high. So these are the disadvantages of this VGG16 architecture. So for that, Google introduced one new architecture that is known as the Inception Network. So it is or Google Net. This is a version 1. It has 4 versions: V2, V3, V2, V3, and V4. It has a 20 layered network, 22 layered network, and the number of parameters is 15 million. 5 million, pardon. And generally it is used for object recognition problems. And using this inception model, uh, the dimension is reduced, and network is this neural network is constructed like that. So GoogleNet has 9 such inception modules, and it is 22 layers deep. And at the end of the network or the architecture, the fully connected layer is replaced by a Glover average pooling, and which calculates average of the every feature matrix. So I will not discuss about the other versions, that is V3. The difference I will discuss about the V1 and V2 or V3. In V3, there is no, sorry, the difference between the Inception V2 and V3 is that in V2, we have factorization and some of the minor changes is put into the V1. And in V3, there is a variant of Inception V2, which adds a batch normalization. So this is the difference between the versions of V1, V2, and V3. Now we'll directly go to the next important architecture, that is the mobile net V2. There are other versions also, that is V1 and V1. I will be discussing on the V2. This has a different concept from other architecture because it has a concept of bottleneck. And this mobile net V2 is built upon the ideas from the mobile net V1, as I told, using the depth-wise separable convolution. But V2 introduced a new features, as I mentioned, that is linear bottleneck has been added with two layers, and the shortcut connections have been done in between the bottleneck. And as the structure is given below, the main purpose of the bottleneck architecture is the bottleneck of the V2 basically encodes the intermediate inputs and the output, while the inner layer, as you can see from the figure, inner layer of the model encapsulates the model ability to transform from the lower level concepts. So such shortcuts enables much faster training and obviously better accuracy. And if I give a small introduction to the architecture, that is V2 contains the initial fully convolutional layer with 32 filters, followed by 19 residual bottleneck layers. And it is very important because this model has optimized and it has been tested on smartphones, and it gave a very good accuracy on the Google Pixel phone for the image classification. So these are all the four most important senior architecture. If you, for the students, if you want to build any type of classification model as per your objective, you can take any of this model as per your complexity of the model, and you can use some transfer learning concepts to remove some of the layers or to add the weights uh, from the this model, and you can build a very good accurate model for your purpose. So that's it from my side today. I hope the session was informative. If you have any questions, you can ask on the YouTube portal. Thank you.
Thank you, Mrinal and Chetan. We'll go ahead and take some time for questions now. So, as Mrinal said, please be sure to type your questions in the YouTube comment box. Okay.
There is one question which has been asked, the tool name which we have used for handwritten digits. So the tool name is 2D CNN visualization tool generated by Regularization University, Canada. So you can Google it, or we'll add it as a comment in further. That you can, it is a freely available tool which you can use to understand the CNN. So I think I answered that question. So I heard that the voice was not clear, so I would repeat. The question was, what tool you used for handwritten digit recognition? So the uh, it is 2D CNN visualization tool generated by Run University, Canada.
If there's no further questions, can we wrap the session?
Yes, Uma.
Thank you, my lord. So, thank you, everyone. for your time and feedback on the session. I'm happy to know that you found the session very informative. So we'll be conducting more advanced session. So the next session is on the topic future trends in automotive HMI. So that is human machine interface. So automotive manufacturers implement a range of human machine interfaces, including voice controls, interior facing cameras, touch sensitive surface, etc. So, HMI or human machine interface is considered as one of the 7 trends that will reshape the automotive industry by 2030. So, HMI connected cars are currently in a transition phase. To get a glimpse of the future, we will share some human machine interface trends in our next session. So, follow us on LinkedIn, Instagram, Facebook to know more about the session. So, thanks again for joining us today. We'll see you next time.